In part 1 of our exploration of the discovery of galaxies, we introduced the Milky Way, the bright diffuse band of light that crosses the nighttime sky, and showed how Galileo resolved it into individual stars with his first telescopic observations, and how the work of Thomas Wright and others showed that it was a flattened disk of stars where we're located roughly near the middle. A second line of investigation was to look at the so-called nebulae, little clouds of glowing light seen in the sky with the first telescopes. People didn't know what they were. Were they clouds of stars, as shown perhaps by Herschel, that some of these glowing nebulae resolved into stars, like the globular clusters, or were they glowing clouds of gas? If work by Kant, and later by Lord Rosse, deepened this mystery and began to make the connection that maybe these distant nebulae, spiral nebulae as seen in Lord Rosse's giant 72-inch telescope, could in fact be other Milky Ways. And so there were two questions that had to be answered. What was the nature and size of the Milky Way, and what were the nature and distances of the spiral nebulae? This is a question that would then carry forward into an essential tension about not only the nature of the Milky Way, but the nature of the spiral nebulae. This is the question we're going to pick up in the second part of our lecture. In 1845, the German philosopher and scientist Alexander von Humboldt revived Kant's island universe idea. Lord Rosse's discovery of the spiral nebulae with his giant 72-inch telescope was one of the catalyzing ideas. In Humboldt's ideas, Rosse's spiral nebulae are other Milky Ways made up of stars. It was Humboldt who introduces the word galaxy to describe these spiral nebulae for the first time. In his idea, and carrying along from Kant's island universe idea, these spiral nebulae are very distant and they are external to our own galaxy. They are literally other Milky Ways. The implication of this idea is that the universe is very much larger than the Milky Way itself. It is a dramatic extension of the Copernican idea. Where Copernicus removed the Earth from the center of the universe and placed it around the sun, and Kant and others, including the Herschels, were later to remove the sun from the center of the Milky Way, so too Humboldt and Kant were going to go even further and remove the Milky Way from its central location and make it but one of many spiral nebulae throughout an immense universe. The observational support, the crucial question we need to use to test this idea, is we need to demonstrate that the nebulae are more distant than the outermost extent of the Milky Way. We need to show that they really are Immanuel Kant's island universes. The alternative hypothesis was put forward based on an idea of Pierre-Simon Laplace in the late 1700s that originally was proposed to explain the formation of our solar system. This so-called nebular hypothesis was that a nearby star passing close by the sun would tidally draw off some matter, gas and material, from the sun. This matter would then settle into a rotating disk, perhaps a disk crisscrossed with spiral arms, and out of this cooling gas cloud, the planets would condense. This was Laplace's idea for the formation of our solar system. So, picking up on this idea, others reasoned the distant spiral nebulae that Lord Rosse was seeing were young solar systems. They were these Laplacian nebulae, out of which the new planets were condensing. If you looked at the sketches of Lord Rosse, and indeed if you ever get a chance to look at a galaxy through a large telescope, they're bright in the center and the spiral pattern is a much fainter disk. One can then extrapolate the idea that, the bright center is a bright forming new star, and the surrounding cloud of gas and dust is its forming solar system. This only works if these things are relatively close by, and no one had a good way to measure their distances. So the key of this is saying that the spiral nebulae are in fact inside of the Milky Way. The implication is that the Milky Way is the entire universe. The Milky Way is synonymous with the cosmos. This is in keeping with the idea of Galileo and Wright, The idea that we are at the center of a starry system, the Milky Way, and that everything we see is that Milky Way. Beyond is darkness and void. The crucial observational test is to demonstrate that the nebulae are nearby and located within the extent of the Milky Way, that they are smaller than the Milky Way and close by, that they are indeed these nebulae forming new stars and planetary systems along with them. The tension, therefore, is between the island universe hypothesis of Kant and Humboldt and the nebular hypothesis of Laplace and others. And the key is measuring distances. There are two crucial distances that need to be measured. The first is to measure the physical size of the Milky Way. That gives us our fundamental definition of internal to the Milky Way and external to the Milky Way. The second is to measure the distances to the spiral nebulae themselves, and therefore measure their distances and, from their angular size, their physical sizes, and to demonstrate either they are as big as the Milky Way and very, very far away, or they are tinier than the Milky Way and located within the physical extent of the Milky Way. This is the observational tension that must be resolved with new observations and interpretations. Biggest advance in this question was made by Jacobus Kapteyn, a Dutch astronomer working in the early 1900s. Jacobus Kapteyn was using photographic star counts along with parallax statistics to measure the size of the Milky Way. It was enabled by a technological advance, the marriage of the technique of photography and with the telescope. When you look through the telescope with your eye, as the Herschels did, and count stars, you're making a subjective measurement. Even though you're counting, it requires a tremendous amount of skill. And indeed, William and Caroline Herschel were among the most skilled observers of their time. But the problem is, the recording device is the human brain. There is no independent record of your measurement except the numbers you're calling out. With photographic plates, the process has changed dramatically because a photographic plate can record what the telescope sees, and you can count the stars at your leisure. It is a repeatable measurement. Different people can count the stars and compare the results. You can apply statistics. How many stars am I missing because of the faint limits of the plates? All of these are details of the art of photographic star counts. The other problem with the Herschel star gauge observations is Herschel's did not have a way to measure the distances to individual stars. Herschel had to make a general statement about the relative size of the Milky Way compared to what he assumed was the nearest star, Sirius. What Herschel didn't fully understand was that stars are all different brightnesses, and therefore the brightness as they appear in the sky is not a measure of their distance. Herschel actually did understand this, but it was the only assumption he had to work with. Kapteyn was able to build on another century and a half of work since the Herschels, establishing the existence of a Hertzsprung-Russell diagram later on in the century, as well as the fact that stars come in all different luminosities. An independent way of measuring geometric distances, parallax, was discovered in 1835 and applied to an increasing number of stars. It was to combine these methods of measuring distances independently of counts and measuring star counts using the then new technology of astronomical photography that was to lead to a revolution in the techniques and allow Kapteyn to take the original star gauge method of Herschel and extend it and greatly improve its power. The Kapteyn model that resulted from these observations is that the Milky Way is a flattened disk, 17 kiloparsecs across and about 3 kiloparsecs thick. A kiloparsec is 1,000 parsecs. We'll abbreviate it as 1 kpc. No, that means 1,000 parsecs. This is quite a leap for Kapteyn. In the early 1900s, the best parallaxes were limited to distances out to about 100 parsecs. That's 1/100th of the 17 kiloparsecs that Kapteyn was measuring. How did he do it? He had to use the statistics of moving groups of stars, so-called statistical parallaxes, combined with estimates of luminosity, comparing to apparent brightness, and estimating luminosity distances, just as we described back in an earlier portion of this course. In doing this, Kapteyn was able to turn his star counts into a physical scale, and this physical scale was immense. 17 kiloparsecs by 3 kiloparsecs. Furthermore, by looking at the distribution of these stars in space, Kapteyn was to show that the Sun is not located at the center of the Milky Way, but is in fact located about 2 kiloparsecs from the center of the Kapteyn model. This would be then the view of the Milky Way and its physical extent and the Sun's location within that Milky Way system in the early 1900s. An alternative method was developed by Harvard astronomer Harlow Shapley. Shapley, instead of measuring the distances to individual stars, which is very difficult and fraught with uncertainty because one does not have a good independent way to know what the luminosity of the star is, and therefore use it combined with the measured apparent brightness to estimate a luminosity distance. Instead, Shapley noted that used star clusters, in particular bright, distinctive globular star clusters. He could make a Hertzsprung-Russell diagram of the globular star clusters, compare that Hertzsprung-Russell diagram to HR diagrams of nearby stars calibrated using parallaxes, and from the position in the HR diagram identify stars of similar type. From that, he could then, using the collective properties of the stars in the globular, estimate the distance to the globular cluster. Combining that with the position on the sky, he could work out their position in XYZ position in physical space, measured in kiloparsecs. This is a slightly modern version of Shapley's distribution in space of the globular clusters. Each of the blue points represents the distance and therefore the position of a globular cluster on the sky. This x and y axis, the y-axis, the vertical axis in this diagram, is perpendicular to the plane of the Milky Way, and this x-axis, the horizontal axis, is along the plane of the Milky Way, and it points towards the brightest part of the Milky Way, towards the constellation of Sagittarius. Instead of counting or measuring the distances to individual stars, he's measuring the distances to individual globular clusters of stars, using their collective properties. If you look at where all of these globular clusters lie, you can see that they cluster over a point in space located far away from the Sun. By Shapley's measurements, the Sun is located off-center from the center of the Milky Way, and the center of the distribution of globular clusters is located about 16 kiloparsecs away towards the brightening of the Milky Way in the constellation of Sagittarius. This is a dramatically different model of the galaxy than was found by Jacobus Kapteyn. Kapteyn found a flattened system with the Sun located about only 2 kiloparsecs away from the center, but Shapley said, nope, if you use the globular clusters and you assume that they are part of the same gravitational system as Kapteyn's system, Kapteyn was only seeing a small part of the Milky Way. The globular clusters show you the distribution of objects in our Milky Way, and the center of that distribution lies 16 kiloparsecs towards the constellation of Sagittarius. Look at the numbers here. The size of Shapley's Milky Way is more than 80 kiloparsecs across, much bigger than the 17 kiloparsecs of Jacobus Kapteyn. The Milky Way is a very, very large system, and the Sun is very far off center. But Kapteyn and Shapley were making a small mistake in their size for the Milky Way. And the reason is that Kapteyn and Shapley were both overestimating the size of the Milky Way because they did not account for the effects of dust absorption. They assumed that space was really just that, empty space. But we now know that interstellar space is filled with gas and dust. This dust plays a particular role. It absorbs and scattered light. Dust is fine particulate matter. Think of it as like light soot, very, very tiny microscopic particles, a fraction of a micron in size, spread throughout the Milky Way along with the gas. In a photograph of the Milky Way, dust appears as the dark regions silhouetted against the bright glow of the Milky Way. What Herschel and others thought were holes in space were shown in the early part of the 20th century, when photographic technologies were brought to play, were not places where stars were missing, but places where our view of the Milky Way is being blocked and obscured by dark clouds of cold gas and dust. We estimate the distance to an object by measuring its apparent brightness, assuming we know its luminosity. The further an object is, the fainter it appears as 1 over distance squared. The assumption that Kapteyn, Shapley, and others were making is that the faintness of a star is purely due to how far away it is from us. But if space isn't empty, and I place a cloud of absorbing dust between me and a distant star, I will make it fainter, independent of its distance, because I'm blocking some of the light. If I ignore the dust, or I don't know that dust is there, blocking some of the light, I will interpret its faintness as solely due to its distance, and therefore I believe the star is fainter than it really is, and I place it further away. So the result of not taking into account dust obscuration, dimming of light that is not due to distance, will cause you to overestimate the distance you estimate based on the apparent brightness and an assumption of the luminosity of the object. Not surprisingly, the more distant you go through the Milky Way, the higher the chances are that your line of sight is obscured by dust, and therefore the worse of a mistake you make. This was first quantified as a problem and solved with the first prescriptions for accounting for dust in the year 1930 by the Lick Observatory astronomer Robert Trumpler. The problem of dust obscuration, making our measurements of brightnesses complicated. They're not just due to distance, but also due to how much obscuring material is along a line of sight between us and the distant object, is one of the key systematic problems of measuring distances in astronomy, and indeed of measuring the luminosities of objects. We have to have a prescription for estimating the amount of dust and obscuration along the line of sight and accounting for it. Even today in the 21st century, as a working observational astronomer, I can tell you that dust is kind of an observational problem. It is one of the pieces of making the measurement that is often among the most difficult to estimate. Now, there's other people, of course. What is one person's problem is another person's source of study. This dust is very interesting to a lot of people because this dust outlines the cold molecular clouds out of which new stars form. But that's a different story that we've already told in an earlier part of this class. Bottom line here is this. Shapley and Kapteyn greatly extended the size of the Milky Way and placed it on a firm observational basis, much better than the work that was pioneering work done by the Herschels in the 1750s. But they overestimated the size because they didn't take into account the effects of dust. Nonetheless, the Milky Way was very big, so we have the first answer. How big is the Milky Way? We now know how to define inside and outside. Now the next question is, how do we measure the distances to the nebulae and say, is that spiral nebula an object inside of our own Milky Way, or is it another Milky Way far, far outside the outer boundary of the Milky Way? The key to measuring cosmic distances, and indeed the key to unlocking the true size of the cosmos, was found by the Harvard astronomer Henrietta Swan Leavitt in 1912. Leavitt was one of the Harvard computers. The job to which she was assigned was to investigate photographic plates taken of the Large Magellanic Cloud from the Harvard College's Southern Observatory in South America. Instead of taking just one photograph of the Large Magellanic Cloud, a series of photographs were taken over successive nights for the course of many years. Most stars shine at a relatively constant rate on human timescales, but other stars are variable stars. They change their brightness in sometimes irregular, sometimes very regular patterns. What Leavitt was assigned to do was to identify those that showed a regular pattern of variation and map out their positions by inspecting plate after plate and looking for the objects whose brightness changed inside the Large Magellanic Cloud. In the course of doing this work, Leavitt made a startling discovery. She found that one particular type of varying star, called a Cepheid variable, named for the star Delta Cephei in our own galaxy, which has a very characteristic pattern of brightness variations. It gets brighter and then suddenly fainter, brighter then suddenly fainter, and that pattern repeats with a very strict period in time. She found that the period of variation was strongly correlated with the luminosity of the star in the Large Magellanic Cloud. The key here is that she wasn't looking at individual Cepheid stars in our galaxy, to which you did not have an independent way of knowing the distance, but instead was looking at a distant cluster, what they thought was a cluster of stars called the Large Magellanic Cloud. This star cloud, which we now recognize as a nearby dwarf satellite galaxy of the Milky Way, has its stars, to a first approximation, all at the same distance away from the Earth. Now, in detail, the Large Magellanic Cloud is thick, so stars on the backside are more distant than stars on the front side. But the thickness of the Large Magellanic Cloud is smaller than the distance. So to a first approximation, you can start by saying, let's assume that all the stars in the Large Magellanic Cloud are at essentially the same distance from us. Then differences in apparent brightness will translate into differences in luminosity because they all share the same distance. And what Leavitt found was if you compared the apparent brightness of the star, shown on the horizontal axis, with the period of oscillation. This is shown on a logarithmic scale. So stars in this cloud here at 0.5 in log period have periods of about 3 days. 1.0 is periods of 10 days. 1.5 is periods of about 30 days. And 2.0 are periods of 100 days. 100 days to repeat this very characteristic pattern of brightening and dimming. And she found there was a very strong correlation. The correlation is in the direction that the pulsation period, which is a distance-independent property, is such that the longer the period, the brighter the star. And if the longer the period, the higher the luminosity. We call it the period-luminosity relationship. If you can measure the period of a pulsating Cepheid star, and the characteristic pattern of pulsation tells you, I'm a Cepheid, you measure its period, then using the period-luminosity relationship discovered by Henrietta Swan Leavitt, you can read off the luminosity. You take the luminosity, you take the apparent brightness, and you can measure the distance. This is a powerful technique because Cepheid stars are supergiant stars. They are intrinsically very luminous, and they can be seen a very, very long ways away. What Leavitt discovered was the key to unlocking distances in the cosmos, an object whose luminosity was bright enough and whose distance-independent pulsation characteristics are distinctive enough that we can recognize them in a distant object and, using the period-luminosity relationship, measure the distance. The Great Nebula in Andromeda, the largest of the spiral nebulae, became the key observational battleground of the 1920s. Finding the distance to Andromeda would provide the fundamental answer to the question, is the Andromeda Nebula inside of our galaxy or outside of our galaxy? And to measure that, you have to measure its distance. The largest telescope in the 1920s was the 100-inch telescope on top of Mount Wilson, just outside of Los Angeles, California. In the 1900s, the Mount Wilson site was not degraded by the bright lights of Los Angeles. Later on, the Mount Wilson site would later be mothballed because the lights of Los Angeles would obscure its view of the sky. It made the sky too bright. But in the early 1900s, Mount Wilson was one of the best observatories in the world. In the 1980s, as an undergraduate student, I had the great pleasure to work with the 100-inch telescope at Mount Wilson. And on nights when the fog obscured the lights of the Los Angeles basin, the Mount Wilson site was truly a superb observing place. The sea air blowing across the mountain made for very, very steady air, which made the images as sharp as possible. And the 100-inch at Mount Wilson was one of the best telescopes of its age. The combination of a good sight and an excellent telescope means it would be possible to be able to potentially resolve the spiral nebulae into individual stars. The search then began to study the Andromeda Nebula using photographic techniques with the 100-inch telescope, and under the best conditions trying to resolve the Andromeda Nebula into individual stars. And once you could see those individual stars, if you could find a way to measure the distances to those stars and find the distance of Andromeda, you would be able to solve the age-old question, are the spiral nebulae nearby or far away? Are they forming solar systems or island universes? The answer came in 1923 by the American astronomer Edwin Hubble, who decisively answered the question by finding a Cepheid variable in Andromeda. He used the 100-inch to take photographic plates, and he was looking for nova outbursts. He identified one here, pointing to it as N. Up here, he found what he thought was a nova, but then he crossed it out and wrote in excited notes here on the 6th of October, 1923, VAR! Exclamation point. This object that he thought was a nova turned out to have a very characteristic period of pulsation, the pulsation that identified it as a Cepheid variable. He could then use the period luminosity relationship discovered a few years before by Henrietta Swan Leavitt and estimate the distance of the Andromeda Nebula. He didn't just use one, but eventually found 9 of these Cepheid variables, and by using the average of these 9 very difficult measurements, was able to estimate the distance to the Andromeda Nebula at a distance of approximately 1 million parsecs. The Milky Way, in its largest extent, shown by Harlow Shapley, was only tens of kiloparsecs, and yet here was Andromeda 1 million parsecs away. When you projected the Andromeda galaxy in angular size on the sky at 1 million parsecs, its extent was also tens of kiloparsecs. Hubble solved the long-standing problem. The Andromeda Nebula was as big as the Milky Way and about 30 times further away than the diameter of the Milky Way. It was another Milky Way. It was a galaxy. And so, by extension, all of the other spiral nebulae, like Andromeda, were island universes, other Milky Ways like the Milky Way, at almost unimaginable distances. The Milky Way, we now know, is one of hundreds of billions of other galaxies throughout the entire universe. In a sense, Kent had the right idea, going from pure reason and the account, a newspaper account, in fact, of Thomas Wright's early idea of the Milky Way, was able to show that the universe was a very, very large place indeed. A galaxy, as we now understand it, is a system of many millions to billions of stars, all bound together by their mutual gravitation. Galaxies themselves are tens of kiloparsecs in size, and the distances between galaxies are measured in millions of parsecs. The universe, as discovered through galaxies, is immense. And just like stars are the fundamental unit of the Milky Way, so we're going to find that galaxies are the fundamental unit of the organization of matter throughout the entire cosmos.